So welcome to Computer Science 305, Programming Languages. This is the final video in the ML series. This is ML Part 4, Part 3, and we're going to be talking about Farewell to ML. So first thing we're going to look at is, so that's really everything we've covered, right? Which was, as I said at the culmination of the previous video, that we've looked at enumerations, data constructors with parameters, type constructors with parameters, recursively defined type constructors, and then before all this, we looked at the basics of the language, basic operators, how do we define functions. We looked at function definitions using patterns, recursion within ML. We looked at if statements. We saw the case statement. We saw basically, and then finally we started looking at higher level functions like map and fold R and fold L. And then we've seen how we can construct and manipulate lists of information as well as tuples of information. We've seen the basic data structures like int, real, character, and string. So you've covered a significant swath of ML as a part of these lectures, and hopefully we'll employ a good amount of it as part of your solution to the ML lab. Now, I will argue that there's a lot more inside of what's going on in ML. For example, things that we did not talk about are records, arrays, references, and exception handling. So we'll kind of talk a little bit about that. And then we'll talk about there's also, interesting enough, inside of ML, support for encapsulation and data hiding, which are basic constructs of object-oriented technique, which includes the capability for structures, which are collections of data types, functions, etc. Signatures, which are interfaces for structures. So, we can think of maybe a structure like an object, an interface like an interface. Functors, which are like functions that operate on structures. And allowing type variables and other things to be instantiated across the whole structure. There's lots of other stuff that we didn't talk about, which is like the standard basis, which is the API, including a vast majority of predefined functions, types, etc. Some at the top level, but most in structures. So you have also like int, real, .math.square root, list.nth. These are all things that we mentioned briefly, but are a part of the actual basis API. If you really want to get into ML, I suggest you acquire a book on ML and really get deep into it. We did not do that here, and I'm not expecting you to have that capability. Other things that we skipped, there's the Xzine ML library for applications that work in the X Windows system. So it's basically it's the GUI framework for ML. There's a compilation manager for building large ML projects, which is a part of the standard ML of New Jersey suite. We did not talk about that, so the tooling associated with standard ML we did not talk about. There's also a huge number of other dialects for beyond standard ML. There's like OCaml, which is object-oriented camel, F#, which is commercialized camel, actually OCaml. And then there's concurrent ML extensions, right? So you can do concurrent programming in ML. And there's things that we're going to talk about in this class. But if you are interested in ML, it is a very smooth language. If you really understand what's going on, you can actually go and investigate that in your own time. If you do, please let me know. I'm always interested in hearing your stories. There are other functional, so functional languages, right? So there are lots of other functional languages. I would say there are actually, with the exclusion of F#, which is the Microsoft functional language. One of the most widely known is Lisp, of course, and then there's also Haskell. And then a lot of people also know Lisp derivative. I think we mentioned it in class during the history lectures, which is called Scheme. Scheme is an MIT derivative of Lisp. And it's pretty easy to learn. If you're interested in functional languages, I would really suggest learning Haskell and Lisp. I also would suggest learning the functional variants from the Java world, which are Clojure, which is a Lisp variant that runs on top of the JVM. and so then compiles to .class files just like Java does, and gives you the ability to interact directly with the Java API as well as built-in closure APIs, and that's spelled, I believe, if you look at the terminal at my window, it's spelled closure with a J. I'd also take a look at Scala, which is the other JVM language that's very functional. I like both languages. I've used both of them many times. They're actually really fun. And furthermore, if you're also interested, I would take a look at the book I'm looking at right now. It's called Functional Programming Patterns, and that takes you through using Scala, Clojure, and one other language. I don't remember which one it is. But and it explores different functional techniques such as tail recursion and as well as more advanced recursion, a variety of other patterns that are typical in a functional programming language. So beyond that, but for the most part, from what I've seen, most functional programming individuals at this time, 2018, are focusing on Haskell. Haskell is a very important language to learn. I would suggest you do if you get a chance. It also has really interesting ties to deep level abstract type theory so abstract type theory is a advance on logic mixed with abstract algebra. So really interesting stuff going on there. Take a look at it if you can. It provides a really interesting approach for solving problems, especially problems today that are, for example, in data science, machine learning. I've seen a lot of interesting, elegant solutions to those problems written in Haskell that are faster, because Haskell is a compiled language. It's faster than, say, Python or Java or C, C++. So just a thought, if you're interested in those types of things, Haskell might be a good solution for you. Anyway, have a great day. I'll see you all in class.